This video begins a 2-day series on Lenz's law and magnetic flux. By the end of the 2 days, you should know the definition of magnetic flux, be able to tell someone a couple of ways to change the amount of flux through a given surface. You should know how Lenz's law applies to conductors, and you should be able to calculate the amount of magnetic flux penetrating a surface. Tonight's video focuses on the definition and calculating the amount of magnetic flux. Magnetic flux, first the definition, is the amount of a magnetic field going through a surface. And the way we think about this is if you were to take, say, a plastic bag and hold it in a magnetic field, and then you counted the field lines that went through the front and out the back, that would be the flux through the plastic bag. And the way we talk about this, because it would actually not be right to just say the field lines going through the front of the bag, and let's say this is just like a little loop of wire, because what if we had some really strange configuration and that field line came back through? So the one going in would cancel the one coming out. And we're also not talking about if we just had like a field line that was just running parallel to the surface and just kind of stuck right there. And so the way we say this is we talk about the magnetic flux that penetrates the surface. It's a weird word, but that's the appropriate one to use, the magnetic flux penetrating the surface. And so when this question says, what are the magnetic flux through this loop of wire? It's actually asking you, if we made like a soap bubble on this ring and just kind of filled in this thing with soap all the way through, how much magnetic flux would penetrate through that soap bubble? What is the magnetic flux through that loop of wire? What's the magnetic flux that would pass through the film of soap on that bubble? Gave you all that because there's actually a history behind trying to figure out what exactly magnetic flux is, and one of the more important things was figuring out which lines we count. Do we count the ones that pass through the edge right here? Do we count the ones just outside the surface? And the way we decided was we're going to pretend there's a soap bubble between the edges of whatever we're talking about, and we just want the lines that would pass through that soap bubble. Okay, so having said all that, let's actually now work on calculating the magnetic flux through that loop of wire. The way you calculate magnetic flux is using this formula, which is fairly intuitive, nothing really strange about it. The formula is phi equals the strength of the magnetic field times the area the field is passing through. And if you were to, say, turn this loop of wire, so if we were to rotate it back a bit so that it's at an angle to the field, not perfectly perpendicular, we would then include the angle between the surface and the field, sine theta. I also need to be careful because I just used the capital letter phi, which is an I and a circle in the middle. However, looking at the AP formula sheet, they use the lowercase phi, which is made by doing a circle, and when you get back to the top, slashing down through it. So this phi, usually with an M, is the symbol for magnetic flux, the number of field lines passing through that surface. And since there's no angle between the surface and the field, because we're just looking at it flat here, if there was a angle, we would have to be shown kind of that loop getting rotated around. And so we'll just do the strength of the field times the area the field passes through. Now since this is a circle, we're going to have to think about how to find the area. It should be pi r squared. And as usual, our units will need to be in the SI system, so we'll have to convert that centimeters to meters. We'll get pi times 0.1 meters squared. And then our field strength is 6 teslas. So now we'll do magnetic flux is 6 teslas times pi times 0.1 meters squared. Got some double parentheses happening. And now I'll just carry out that calculation. And out of this, I get that my magnetic flux is 0.18. I'll go ahead and round there. Webers. So the unit for magnetic flux is Weber, which is W lowercase b put together, so it can be kind of strange. It often looks like two units together, or maybe like the W is a prefix, but it's big W, little b. A Weber is also equal to a Tesla meter squared, or if I remember correctly, a volt second. Or carrying it even further is also a joule per amp. The one you'd be most likely to be asked about is the Tesla meter squared, just because that's what comes straight out of the equation if you multiply the units together. And then Weber is the official unit. And by the way, Weber is spelled like Weber, W-E-B-E-R, Weber. After I finished making this video, I realized I made a small mistake. And it's small because I didn't actually use it in the example. But the mistake that I made in the example, or sorry, not in the example, but in the first part, the magnetic flux would not have sine in it. It would be cosine. And that's because as the angle gets bigger, we want the magnetic flux to get smaller because there'd be less of it passing through. Sine would actually have the flux getting bigger as the angle got bigger. Cosine has the flux getting smaller as the angle gets bigger, and that was my mistake. Next I want to show you some interesting consequences of when you have current going in a circle, and we'll use this more tomorrow. So I have current flowing clockwise through a loop of wire here. What's the direction of the magnetic field at the center of the loop? So to start out, whenever you're given a problem like this, where you're not sure where you need to do the right-hand rule, just do it at a bunch of places. So I'm going to try 4 places. I'm going to check here, 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 and here, see what the magnetic field is from each place, and then see what happens when I add them at the center. So if I'm checking maybe first the front place, so my thumb would point to the left, that's the way the arrow is pointing, my fingers would curl, and then at the center of that circle, it'd be pointing down. Okay. Now if I check at the back, if I point my thumb to the right and curl my fingers in, at the center of that circle, again pointing down. Now if I check over here, if we continue the pattern of the arrows, I'll be pointing this time out of the page, curl my fingers, and I get down again. And over here, back into the page, curl my fingers, and then I got to rotate my hand, and at the center they're pointing down. So the magnetic field at the center of the loop is down, because it looks like if I checked at every place, I'd keep getting down. Well, here's a neat consequence. Take your fingers, not your thumb, and curl them the way the current is going. And notice, if you curl your fingers the way that current goes, your thumb is pointing down for your right hand. And so this is actually called right-hand rule number 3. If you curl your finger in the direction of a loop of current, so it's only for current going in circles, only time it works, your thumb points in the direction of the magnetic field lines. So I curl my fingers kind of toward the back, and then my thumb points down. One nice use of this is if you ever build an electromagnet from a loop of wire and, say, an iron nail. We can figure out where the south pole of the electromagnet is located. So let's try this. We have several loops of current, so these loops up here around the iron nail would be loops of current. And we have a positive and negative end of the battery. Now we know electrons will leave the negative end of the battery, but because we're thinking current, current would actually be going from positive to negative, so the current would be this way. That's just by convention. Never bothered to change it. And if we follow, you actually got to follow that path. Notice it first goes back behind the nail. So you'll take your right hand and curl it like it's going back behind the nail. And then your thumb should point to the right, meaning that the magnetic field lines would point out this way. And then also, because this is basically forming a magnet, as the problem tells us, the electric field lines would then point back toward the other end of the magnet. But even if you don't get that part, you can still get the answer correct from, okay, the magnetic field lines point this way. Remember that magnetic field lines point away from north, because a compass north end would point toward south. So that means that over here must be the north end of the magnet. And even if you didn't understand that the field lines would loop back to the other side, you could still say, oh, well then the other end must be south, because there can't be any monopoles. You always have to have a north and south pole. But your thumb points out when you curl your fingers, meaning the field lines point this way. And the field lines point away from the north end, meaning that this must be the north end. And so the south pole, the question asks us, is located closest to point D, because that looping wire is generating a magnetic field. So that's how this thing becomes a magnet, is that loop of wire creates the magnetic field. Finally, and this is going to be the big one, and you're going to see lots of examples of this in tomorrow night's videos. Anytime you change the amount of flux through a surface, so if I take this loop of wire, shown in the picture, that's the black loop is the loop of wire, and I start shoving it into a magnetic field, some interesting things are going to happen. That magnetic field is going to push around the charges in that wire, because remember, we've now got electrons and protons in that wire, and they're now moving. So they're going to get pushed around, and they don't like getting pushed around. So their inertia is actually going to do something really interesting. And I do, in my head, relate this to inertia. And I actually haven't found a lot of videos looking through, just hoping to see someone doing a demo and talking about this way. I haven't seen a lot of people relate this to inertia, but I think it's really helpful. The charges in that loop won't want to move, and in fact, they're going to not want to move so bad, they will actually generate a magnetic field that pushes back on the field that's being shoved toward them. So from their perspective, that field is being shoved toward them. You're trying to force more flux through this loop. More flux is trying to penetrate the loop, and the loop, the charges in it, don't want more flux to go through. So they're actually going to generate a magnetic field the other way to push back. And so right now we have a magnetic field going into the page, and there's more and more of it going into the loop. So this rule only works for changing magnetic fields, because inertia says we resist change. Everything resists change. So anytime your flux is changing, if you're doing something to increase the flux, like here, as we shove that loop over, more of the field, which is contained to just this kind of square or rectangle with the x's, more of that field will be passing through the loop. And so to resist the field into the page, the loop will create a field back out of the page. The only way it can do that is to generate a current around itself. And so we've got to figure out which way that current will go. Well, the rule I showed you a second ago applies, except backwards. So I'll put my thumb in the direction of the magnetic field that the loop is generating out of the page. My fingers will curl in the direction of the current, meaning that this loop is generating current this way to resist the change in the magnetic flux. Now, once that loop is in here, so sometime later when the loop is actually in the field and not moving, the current will stop. It's only while the field is changing, because this is inertia expressing itself, saying, no, I don't want this change. And so it actually generates a magnetic field the other way by causing a current in itself. Maybe rewind 3 minutes and watch that again, but take a second to think that through. A loop will not want the magnetic flux through it to change, and so it will actually generate a magnetic field to prevent the change, because it will cancel out the change. This is called Lenz's law. Lenz's law says the induced magnetic field inside any loop of wire will act to keep the magnetic flux penetrating the loop constant. And this is about inertia. Those charged particles don't like being shoved around. They don't like how the magnetic field is trying to change their movement. And so they will actually create a magnetic field to resist the movement. And it's really just one of the strangest things, that inertia is that deep in the universe that a loop of wire could actually generate a magnetic field to keep the fields through it from changing. Just think about that for a second. That's how the universe behaves. Things in the universe dislike and hate change so much that just a loop of wire, just like if you took some copper and coiled it up, it can generate magnetic fields to keep itself from changing. That's how much it hates change, that it will generate a magnetic field to keep changing from occur. It's crazy. And like I said, relating this to inertia helps me a lot. Those charges in that loop don't want to change, and so they will create a magnetic field. And then the tricky part is just, okay, so if the field is increasing into the page, because as we shove this in, there'll be more and more field into the page inside that loop, then the loop will make a field out of the page, and to do that, there must be a current running this way by the right-hand rule. Thumb points out, current goes around. I know I rambled on about that for a long time, but it's really cool to me that the universe behaves this way, and hopefully inspired you to think about it some more. We've got some cool demo videos for tomorrow where you'll see this some more.